Okay, so now we're at lesson 2. We're looking at binomial distributions. So Bernoulli trials are independent trials that have two possible outcomes. So success or failure. And the probability of each outcome is the same for each trial, since the trials, I should say trials, not trails, are independent. So trials with replacement. So think of our examples from previous units where we looked at pulling a card out of a deck and putting it back. When we put it back, it didn't change the probability. It remained the same. So there's replacement happening. So each trial is not dependent on the previous trial. So another example was tossing a coin, heads and tails. That would not depend on the previous trial. So for any trial, the probability of success, so P success equals 1 minus the probability of failure. Okay, so it's a complementary event. So this here is a complementary event. Okay, so the probability of the likelihood of success is equal to 1 minus P of failure. So this is called also binomial distribution. So an experiment that consists of n Bernoulli trials. The purpose of the experiment is to determine the number of successes. The probability of a given success is found by using the following general formulas. This is our formula here. And we look at n choose x times the probability of the success. So P would be the probability of success to the exponent of x, the number of successes required, and Q to the power of n minus x, so the number of trials minus the number of successes. And just a reminder, the capital X is your random variable, and it's equal to how many successes that random variable has. So remember, like previous lesson, the random variable, we were interested in how long people were waiting in line, how many women made a committee. Those were our random variables. And the number of trials is the number of opportunities for success. So how many times am I repeating this experiment? So here we have a survey of families is taken. Find the probability distribution for the number of girls in a family with 4 children. So I guess the number of successes required, we would want to have 4 girls. So we're going to say let X represent the number of girls in the family. Okay, so 4 girls would be a success. So if we have X, we could have 0 girls, we could have 1 girl, 2 girls, 3 girls, or the success, which is 4 girls in the family. So that means our n would be equal to 4. And what I want to say here. So the point of interest would be the random variable x, which would be having 0, 1, 2, 3, or 4 girls. So when we add those up, let's look at finding P. So the probability P would be of having a girl. That would be our success, 0.5, and that would be having a girl. And Q would be 1 minus 0.5, which would be 0.5. That would be having a boy. So we are going to let's write out our general formula here of P is equal to capital X equals X. We can replace now n. We know n is 4 because we want 4 children. Choose X. So the number of successes there, times 0.5 to the exponent of x, and 0.5, if we have a boy, to the exponent of 4 minus x. So now we need to find out all the different probabilities here. So the possibility of I'm not going to have a lot of space here. I'm going to try to write it a bit smaller. P of x equals 0, so I'd have no girls. So that would be 4 choose 0 times 0.5 to the exponent of 0, 0.5 to the exponent of 4. I'd have all boys. We're going to do it for x equals 1, 2, 3, and 4. So now we just go through, it takes a bit of time just to put in our work here. And then 0.5, 4 minus 1 would be 3. And then you'll do some calculator work to figure out your answers. So this would be 2 boys, 2 girls. And the last one, 4 choose 4, and that would be number of girls. So you're going to take some time here to figure out each one. You can use your calculator to find out the number of girls and the probability of each situation. So here the first one, 4.4, you're going to do 4 choose 0 times 0.5 to the 0, 0.5 to the 4, and that's going to give you 0.0625. This would be 0.25, 0.38, 0.25, and 0.0625. So if we did the summation of all of these probabilities, they would all add up to 1. Remind you, we did round here, so that is going to be a little bit off. Okay, so let's look at the next example. A pair of dice is rolled 20 times and the sum is recorded. So think of our previous units where you had the charts. You have 2 dice. They are fair die, so they go up to 6. Okay, and the pair of dice is rolled 20 times. The sum is recorded. So we're looking at the sums. Find the probability of double 6s occurring exactly 2 times. So I'm rolling these dice 20 times. I want to find the probability of rolling it exactly 2 times. Okay, so that's your key word here. So just a reminder that how this chart works, I would have, say, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. Okay, so I'm looking for that combination there where I roll the 2 dice and I get 6 and 6. So that means when I'm rolling my dice, I can get 0 double 6s. I can get double 6s once, twice, all the way up until, if I was really lucky, I would roll 20 doubles of the 6. But here in this question, they're telling me exactly 2 times, so I'm looking at 2. So we're going to say let x, we're going to always define, so let x represent the number of double 6s. So let's just do some defining of our statement of our variables here. We know n, we have 20 trials. The probability of success, remember we have 36 combinations there, would be 1 out of 36, because I have that 6, 6 happens once out of 36 possibilities, which means that would be, if I were to decimal, 0.028. So my Q would be the probability of not having a success. So it would be 1 minus that, which would give me 35 out of 36. All the other possibilities that are not the double sixes. So it's 0.972. So let's write out our formula. So P equals the random variable, which is equal to my successful trials, would be 20, choose X, times the successful trials would be 0.028 to the power of X times 0.972 to the power of 20 trials minus X. So now we can sub in our values. So we want exactly 2 rolls of double sixes. So when I do that, that means I would have X would be 2, 0.028 to the exponent of 2 times 0.972, 20 trials minus the 2, which would give me 18. So this here would give me 190 times 0.00078 times 0.5998. So in total, I get 0.089. And this is probability. So therefore, I have limited space here. Therefore, we have an 8.9% chance of getting double sixes. That's our success. 2 times. When a pair of dice is rolled, (20) times. Good. So now we're going to say find the probability of rolling at least 2 double sixes. So the first one was exactly 2. At least 2 would mean I can roll, let's change my color here. I can roll it twice, 3 times, 4 times, 5 times, all the way up to 20 times. So that would take a lot of work to show if I did it directly, right? So if I did it directly, I'll show this here on the side. If I did it directly, I would do P at 2 plus P at 3 plus P at 4, all the way up to P at 20. Okay, that would be a lot. So instead, we're going to use complementary. Okay, so the complementary event. So we're looking for the probability that our X is greater than or equal to 2, because it says at least 2 double sixes. So I can have 2 all the way up until 20. So what I would have to do there is take 1 minus the probability of 0 double sixes being rolled minus the probability of 1, because these are the cases that we don't want. Okay, so it's a complementary event. So this makes it a little bit easier, because now I can do P at 0, which is 22, choose 0, times 0.028 to the exponent of 0 to the exponent of 20, minus, now we're going to do 20, choose 1. If I rolled it once, that wouldn't be a success, because I need to roll it twice. So 0.028. So if you use your calculator, this is a lot less calculations as opposed to doing 18 of these calculations. We only do 2. So we have 1 minus 0.57. And think about 20, choose 0 is 1. 0.028 to the exponent of 0 is 1. So you just have to find that bracket there. Minus 0.33. And that gives us 0.11. So you have an 11% chance of getting at least 2 doubles 2 double sixes. When a pair of dice is rolled 20 times. Okay. So be aware of the complementary event because that will make your life easier. All right, onwards. In a manufacturing process, it is estimated that 1% of the products are defective. If a client places an order for 25 products, what is the probability that no more than one of them is defective? So no more than one of them is defective. I know this is backwards thinking, but your success here is being defective. We're trying to figure that out. How many? We're going to have no more than one. So let's say let X represent the number of defected items. And remember, you can have our X is equal to, you can have 0 defected items, 1, 2, all the way up to 25. That would mean all the items, all the products purchased would be defective. So our N is equal to 25. The probability of success, here we're looking for it to have 1%. So that's our success. 1% would be success. That would be 1%, which is 1 over 100, and that equals 0.01. Only 1% defective, that would be success. The alternative would be 1 minus 0.01, which is 0.99. So we can write our formula. Just before we write the formula, we're going to think, is this a binomial? Is it a binomial distribution? And yes, it is, because if you choose a product and it's defective, it's not going to change the overall outcome of the next product. Okay, so these are independent events. This is a binomial distribution. It does not affect the next item. So if I have one item that's defective and I pick the other item, just because the other item was defective doesn't mean the one I have next is going to affect that. So that's it's called Bernoulli. Bernoulli trial. So we can write out, we want no more than one being defective. So that means we need our probability to be X is less than or equal to 1. So we can have the probability of X being 0. So no items are defective. Or, so or is plus. Or one item is defective. And so we can use our formula. 25, choose 0. Probability of success is 0.01 to the exponent of 0 times 0.99 to the exponent of 25 plus 25, and one item is defective, meaning we have a 0.01 success to the exponent of 1 and 0.99 to the exponent of 24. Again, some calculations here. 1 times 1 times 0.778. And then 25, choose 1 would be 25 times 0.01. 0.99 to the exponent of 24 is 0.786. And using your calculator, you can multiply and then add those two together. So 0.778 plus 0.196, which gives you 0.9745. So therefore, I know it's a bit counterintuitive here, we have a 97.5% chance of having no more than one defective product when 25 products are ordered, which is good because you have almost a 98% chance of not getting a defective product out of 25 items. The last thing here is the expected value. So we did this in lesson 1 a bit, but just a reminder, this is not a probability. It's not a probability. We're overall what is expected to happen, and we're looking at the units of the original problem. Units of original. So we have E times X, number of successes, equals N is the number of trials, times the probability of success. So let's look at this example here using that formula. A baseball player has a batting average of 0.320. So the probability of hitting, this is the probability. That would be a success. For a particular game, he will go up to bat 3 times. So that's the number of opportunities. So that means N is equal to 3. The probability of success, I hit the ball, would be 0.32. The alternative, not success, would be 1 minus 0.32. We know this is also a Bernoulli trial, because if I hit the ball once, it's not going to affect if I hit the ball again. Or if I miss and I go to bat again, I can still hit the ball again. So we're going to use our formula, P equals X equals X. We're looking for the probability here. Okay, we're not looking for the expected, that's next. Probability is 3 choose X. Our success is 0.32 to the exponent of X. Not being successful, 0.68 times 3 minus X. So what is a probability that he will not hit? Okay, so not hit means he's got no hits. So that's a P of X equals 0. So if that X equals 0, then that means we have 3 choose 0. And we have 0.32 to the exponent of 0 times 0.68 to the exponent of 3. So he's not getting any hits, which would mean we have 1 times 1 times 0.3144. So we get 0.3144. So the probability that he will not hit would be 31.4% chance of not hitting. When at bat 3 times. And now the expected number of hits would be using our little formula here, E at X equals N times P. N is the number of trials, so we have 3 trials. The probability of success would be his batting average. And our nifty little formula there, 3 times 0.302 gives us 0.96 hits. Those are the number of hits. So therefore, we're looking at discrete. This is discrete. So we can't have a 0.96 of a hit. It's 0 hits or 1 hit. So we approximate this to be 1 hit because of our discrete data. Therefore, we'd expect 1 hit when he goes to bat 3 times. And that is lesson 2.